Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a mini-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 2, A History of the Atom. Episode 5, The First Chemical Revolution. Our story with this episode begins with a problem. Actually, it's two problems that are really the same problem, but in 1700, no one really knew that. And if we're going to be totally complete and consistent, it's a whole class of problems that are due to the same underlying physical cause. But we'll get to that. So in 1700, the intellectual energy of the Renaissance has played out and had matured into something we call the Enlightenment. The scientific revolution, starting with Copernicus, had culminated in the masterwork of Isaac Newton, the Principia, and the stage had been set for the Industrial Revolution to begin. The great powers of Europe had settled into something more static, and so there was less conflict. National governments had risen to meet the challenges of providing both economic growth and national security to their various peoples and regions. This new, less chaotic state of affairs led to increased material production, which made the lives of most people better and gave rise to a much larger professional middle class with the resources and interest to pursue knowledge and answer questions. Okay, enough with the historical context. What was the burning question that was on the minds of the alchemists who were quickly becoming chemists? One of the big questions of the day was, what's going on when things burn? See what I did there? The process was and is called combustion, and it's one of the things that we're all pretty familiar with. It's something that human beings have been curious about since the dawn of history. Anyone who sat around a campfire or hearth is sooner or later drawn into the dancing flames and glowing coals. It's an almost mystical thing to see wood transformed into smoke and ash while warmth is produced. In this, one can understand the alchemists' continuing attempts to produce similar transmutation in a controlled way. Another question had to do with a process that at the time was called calcination. Calcination is what happened when an alchemist would take a fairly pure sample of some metal and heat it. This heating would cause the color of the metal on the surface to change, sometimes pretty significantly depending on the metal. Since both of these phenomena seem to be involving or changing or transmuting one substance into something else, they were really of great interest to alchemical investigators all the way back to the classical period in Alexandria. Through the Hakim of the Arabic Golden Age, across North Africa, into Spain, and then more broadly throughout Europe, the investigations and writings of the alchemists, often almost incomprehensible, tried to understand what was taking place in these commonly observed phenomena. It was only after Boyle, however, that an emphasis on systematic investigation involving rigorous measurement began to take hold. Once that happens, however, it's off to the races. So let's start with the thinking of the time. Aristotle's ideas of four elements had failed to get anyone very far for about 2,000 years, so it was time to come up with something new. Now, back in the introductory series of this podcast, we talked about this process by its more fancy name, what we called hypothesis modification. Now, as we said back then, it's really hard to just completely throw out an idea, especially if it's worked in some way. When you observe combustion, it certainly looks like something is leaving the wood with all the smoke and fire that leaps up into the air. So, it was thought that maybe something else besides fire was actually leaving the burning object. The stuff ended up being called phlogiston, which was taken from the Greek word for burning up, which, by the way, I think is one of the most fun scientific-ish words to say, phlogiston. The guy who first came up with this idea, though we didn't actually call it phlogiston, was a historically epic snake oil salesman, Johann Joachim Becher. While we don't have time to talk about him, this guy was involved in every conceivable scam one might think of in the middle of the 1600s. The idea is that when something burned, phlogiston left the system, leaving behind only the ash of the original object. When something calcinated, the same thing was going on. Phlogiston was leaving the metal, which changed it into the tarnished stuff that was left behind. The more heat that was applied to the metal, the more phlogiston would be released, the faster the metal would tarnish. It's a pretty simple and interesting idea. The problem with this, though, is that the mechanisms for how phlogiston did the leaving weren't very well understood, if at all. One other problem is that it had been known about through the work of metalsmiths that when you heated a metal, it actually gained weight rather than lost it, which made it pretty hard to think that the metal was losing something. And finally, there was a third question about how the phlogiston actually got into the substance in the first place. You got to answer those questions if you want to take the hypothesis seriously. Now, the best known advocate for the phlogiston hypothesis was a German by the name of Georg Ernst Stahl. His reasoning went something like this. Okay, sulfur burns in a flame and produces sulfuric acid as it does. Therefore, sulfur consists of sulfuric acid and phlogiston. If the phlogiston could be restored to the sulfuric acid, then the substance would be converted back into sulfur. That's an interesting hypothesis, so we got to test it. Stahl recognized that charcoal, when burned, could do this while leaving only a very small amount of ash, so he concluded that charcoal must be pretty rich in phlogiston. So, Stahl heats a treated type of sulfuric acid with charcoal, and lo and behold, he got out of that reaction what was called liver of sulfur at the time. I know, strange. And that liver of sulfur was really sulfur plus the stuff he had treated the sulfuric acid with to begin with. That's actually some pretty good work right there, and it went a long way to establishing the phlogiston hypothesis. While there were advocates of other ideas and the calcination weight gain problem still had to be solved, Stahl was persuasive and the idea gained a lot of support in the following years. What was still difficult was trying to actually capture some of this phlogiston stuff. It seemed to disappear right into the air, odorless, colorless, and tasteless. Now, one of the things Stahl was able to do, though, is Stahl was able to establish in his hypothesis that that's why you couldn't do any of these things in a vacuum. What Stahl said is that you had to have air present as a mechanism to absorb the phlogiston. He also explained that when something was burned in a closed container, the flame would go out because the air would become saturated, or what he called phlogistated. Now, if this was the case, it was pretty obvious that there needed to be better examinations of air to understand what was going on. As chemist Karl Shell would later say, quote, "I soon realized that it was not possible to form an opinion on the phenomenon of fire as long as one didn't understand air." And so this brings us back to the pneumatic chemists and a specific guy by the name of Joseph Black. Now, Black was a Scot born in France, and he was trained as an MD back in his native country of Scotland. Black noticed an interesting phenomenon while doing research for his thesis about treating kidney stones. What he found was that if he treated a substance called magnesia alba with an acid, the material would bubble. Now that meant it had to be releasing a gas. Now, if you recall from our last regular episode, Helmut had identified a class of substances that seemed to be different than the element of air, which of course is what we breathe. At Helmut's time, air was thought to be just one thing, not the mixture we know it to be now. His work had shown that there were other substances that were like air, but that might have different sorts of properties. Black realizes that he's found one of these things. Now, before we move on, this is a good place for a moment of commentary. What we're seeing here is the first tangible result in chemistry of Boyle's insistence on meticulous investigation. Black's got this stuff, magnesia alba, and as a good chemist, he realizes he needs to learn as much about this stuff as possible and then document and catalog what he's learned. That means he needs to experiment with it and on it by exposing the substance to all sorts of different reactive agents to see if anything happens. In this case, pour several different types of acid on samples of magnesia alba, and then observe and record what happens. This is exactly what Boyle had written about real chemists doing based on the scientific method of Francis Bacon. The individuals we will discuss in this podcast are exemplars of Bacon's method carried out in Boyle's program. Priestley, Cavendish, Shell, and Lavoisier all owe a great debt to following Boyle's imperative that research must be meticulous. It is why they are remembered, even though they often only expanded on the research of other less well-known investigators who, since they neglected Boyle's advice, missed following up on key observations that they made and thus missed the discoveries that were right in front of them. Okay, back to Black in his lab with his white magnesium. I'd like to spend a little extra time here because even though his contributions are only the beginning of the story, they are clear and concise and thus easier to follow in some cases, and his biography and work are often neglected in favor of the more pivotal biographies of Cavendish, Priestley, Lavoisier, and such. I find Black to be a fascinating figure, so I like to tarry here a bit before jumping back into the bigger narrative. So what happened? Well, in every case, bubbles. This leads Black to form a tentative relationship that says whenever he reacts magnesia alba with an acid, he gets a gas released in the reaction, and what's left behind is something known as a salt along with water. It turns out that through experimentation, Black finds that there's an entire group of substances that we now call carbonates that do exactly the same thing when treated with acids. It's kind of the same, or it's the same kind of reaction you can do in your kitchen with baking soda and vinegar. Take baking soda, mix vinegar, and voila, foamy, bubbly goodness. We've all seen it. Now, what happens next is pretty darn cool. Somewhere along this line of investigation, Black applies a strong heat to magnesia alba. Kind of like calcinating a metal, but since this stuff isn't a metal, it's not quite the same thing, and the stuff doesn't tarnish. Great. Next, he takes the heated magnesia alba and he dumps acid on that. And what happens? Well, nothing, sort of. He still gets the salt and some water, but no bubbles. Now he's got something really interesting going on. Well, others might decide to move on with their research on how to use this stuff to treat kidney stones. Black does what Boyle says a good chemist to do. He creates a detailed research program to see if he can try to figure out what's happening. So, what is Black going to do next? Coming up with a hypothesis, he says that the acid is liberating the gas from the magnesium alba, and it's the same gas that gets driven off when magnesia alba is heated a lot. Excellent hypothesis. But now he's got to test it. So how? Well, the first thing he tries to do is bubble the gas through water in order to trap the gas, but the problem is the water just absorbs the gas, which means he can't do anything with it. Bummer. Then he hits on an idea. Why not just work with the reactants and make really careful measurements there? Well, that'll work. Okay, so he does that, and the measurement that turns out to be the most important has to do with the weights of things. In the first experiment, he weighs the magnesia alba and the acid both before and after the reaction. And it turns out they weigh just a little bit less after the reaction. And he figures that the difference must be the gas that's leaving the system. Okay. Next, he does the weighing thing again, but with the heating process in the middle. Again, the stuff before all the work, heating the magnesia alba and then dumping the acid on it, weighs a little bit more than after all of that stuff. However, the clincher is that the difference between the before and after is the same in both processes. Bam! Heating must be driving off the gas from the sample just like the chemical reaction with the acid does. Not only that, if he adds the same weight, of a mild alkali, remember Jabir and the ashes, back to the salt water mixture left over after either process, he gets the original amount of magnesia alba back. While Black doesn't really seem to have realized it, he's just proved the law of conservation of mass. But wait, there's more. Black's really curious about what this gas might be, and so he starts experimenting on it. One of the things that he does is that he bubbles this gas through something called lime water, or just lime now, and the lime water turns cloudy. Well, that's interesting. He thinks, I wonder if anything else does that. Now, if it does, Black's found a way to detect this new gas in other processes. So the first thing he does is he takes the gas products from combustion and he bubbles them through the lime water. Cloudy, just like the magnesia-alba acid reaction. Then he takes the gas products produced by the fermentation of grain, i.e. beer making, and he bubbles them. Cloudy. Then he takes the air that a person breathes out after breathing in and, wait for it, cloudy again. So cool. In further experimentation, Black determines that this new gas, which he calls fixed air because it seems to have been fixed in the pre-reaction material before being released, doesn't support respiration itself, even though it's a byproduct of it. Put a living thing in a jar full of this gas, and the living thing dies pretty quickly. Interesting, especially if you're a physician like Black. Now, at this point, Black publishes this work, and it makes a pretty good little splash in the scientific communities of Scotland and England. Unfortunately, life circumstances conspire to keep Black from pursuing his research much beyond this point. He takes over a medical practice and a professorship which eats up most of his time for research, with the teaching and administrative responsibility. Eventually, he moves to similar positions in Edinburgh, and while there, becomes an active member of the philosophical community in Edinburgh itself, along with guys like economist Adam Smith and philosopher David Hume. Now, it would have been pretty amazing to have been able to sit around the table with these guys while they discuss the intellectual issues of the day, I think. A few more notes about Black and his scientific work. He invented the first analytical balance for use in chemistry, a tool that aided his and everyone who follows work immeasurably. He also developed a theory of latent heat that helped explain things like freezing and boiling. He's said to have been an excellent and engaging teacher, touching on the Aristotelian theory when absolutely necessary and rejecting the four elements model entirely. He focused on the results of practical chemical work. In fact, if the old adage that talent of the teacher is best judged by the accomplishment of his or her students, then high praise must be given to Black, as it is one of his pupils who will really bust this pneumatic chemistry thing wide open. That student's name was Daniel Rutherford, and he continues Black's investigation into gases. What Rutherford is able to do for the first time is show that what has been called air is actually a mixture of at least two different gases. This, of course, is a nail in the coffin of Aristotle's elements hypothesis. Air can't be an element if it's made of a mixture of other stuff. Next, Rutherford follows Black's work and shows that respiration takes one of the gases in air and converts it into Black's fixed air. He then bubbles that through lime water in order to take out the fixed air and experiments on the gas that's left over. What he finds out is that there's a lot more of it by volume than the other gas, and that it doesn't support life. Rutherford calls the gas that supports respiration good air, and the stuff that doesn't phlogistated air. His idea is that the process of respiration has released phlogiston that has saturated the rest of the gas so that it can't absorb anymore. Because of this, Rutherford says that the process of respiration can't proceed, and so the animal placed in the phlogistated air dies. As you can see, this is all very, very supportive of the phlogiston hypothesis. The third British empiricist in this story of pneumatic chemistry is a guy by the name of Henry Cavendish. While Cavendish will be known for a number of other scientific contributions, especially in the field of physics, it is his work in factitious airs that we are interested in here. Factitious airs were gases that were fixed in some material, but that could be freed via chemical reaction or some other process. Black's fixed air was just one such gas. Another was a gas that was created when various metals were reacted with certain acids. It was found that this air would burn very vigorously in regular air, this gas, I should say, would burn very vigorously in regular air, and was called at first inflammable air. For a time, Cavendish didn't do much else with this discovery, at least until the work of our fourth Brit is made known. This guy, whose name is Jason Priestley, was an Englishman of many interests and talents and a bit of a contrarian. While we don't have near enough time to delve into his work outside of pneumatic chemistry, I expect there will be a supplemental episode devoted, in part, to his tumultuous life. Priestley's work in pneumatic chemistry was kicked off when he hit upon the idea of bubbling gases through mercury instead of water. This allowed him to exclusively isolate Black's fixed air as well as Rutherford's phlogistated air. Using this technique, he was able to isolate two gases that were produced when nitric acid was reacted with metals. One was a well-known brown fume, but the other had been undetected due to being colorless. Priestley called this nitrous air and found that when he filled a container with it that also had iron filings in the bottom, another gas was formed that would enhance combustion that was given the name dephlogistated nitrous air because Priestley thought that the interaction with the iron filings had removed phlogiston from the gas. Priestley also observed that the brown gas was actually formed only when the producing reaction was done in an environment with regular air. What he found was that if he kept track of how much regular gas was in a container when he started, the vapor that turned into brown gas reduced the volume of the air by about 1/5. This gave him a way of telling how much good breathable gas was in a common air sample in a fairly quantitative way. During this time, Priestley experimented with a number of different reactions by collecting the gases they produced and then doing research with those. One of the gases he got was produced by heating strongly a sample of mercury ore. When testing this, he found that the new gas had even more ability to support combustion than his dephlogistated nitrous air, and so he simply called that dephlogistated air. He found that it supported respiration, first by testing it on 2 mice and then on himself. Priestley's work during this time was prodigious, and between 1774 and 1786, he wrote a 6-volume work titled Experiments and Observations on Different Kinds of Airs. Now, this is where Cavendish enters back into the picture. Keeping track, got Cavendish, then Priestley, now we're back to Cavendish. And as a side note, Cavendish was the very stereotype of a scientist that I tried to dispel in the misconceptions episode. Hey, stereotypes often have their basis in reality. He was a taciturn man of few words, bad fashion sense, and an obsessive devotion to doing science meticulously. The work I'll describe here was actually the result of several years' worth of refining both his experimental techniques and those who had gone before him. His notebooks speak to his devotion to precision in his work, and it was through his painstaking accounting of every single observation and variation in his data that his results were established beyond criticism to the scientific community in London. What Cavendish did was took his inflammable air and Priestley's dephlogistated air and put them in a container together. He then applied a spark and got a good bit of heat and light and some leftover water. Actually, the first time he did it, he blew up his beaker. But, you work on your method, right? From this, Cavendish concluded that all of the dephlogistated air had taken in all of the inflammable air to produce the water, which led him to say that inflammable air was just pure phlogiston. The other result of this investigation was to show that water was a combination of two substances, which meant it wasn't an element. And if you're keeping track, that's 2 of Aristotle's 4 that have now been removed from the list. Cavendish also found that the water that had been produced contained a very small amount of nitric acid. He summarized correctly that this had come from Rutherford's phlogistated air that hadn't been completely removed from the dephlogistated air sample. So he sets about to, doing that better, to taking care of everything and to measure everything. And once he removes all these impurities, he finds that he still has something else left over that he can't account for. Now, volume-wise, this unidentified gas takes up about 1% of the original air sample, and Cavendish couldn't get it to react with anything that he tried. Now, it's going to take over 100 years before someone's going to finally figure out what that stuff was. What Cavendish and Priestley don't know is they're not the only ones working on this last piece of the puzzle. Two others were on the same trail of looking at these same sorts of reactions, one a bit earlier, one a bit later, but all were working somewhat, if not completely, independently of each other. The first was Karl Shell, a Swedish pharmacist who observed that combustion reduced the volume of a gas and that what was left behind was less dense than common air. He reasoned that the phlogiston released by the combustion had combined with a component of the common air, and that the combination had left the system as heat. Shell called the unknown component of common air fire air, and worked to isolate it through a series of chemical reactions. When he did so, it supported vigorous combustion, and when it was added to the sample of unbreathable air, it made the air breathable again. So, using a very different method, Shell had found the same substance that Priestley had, and by some accounts he had done it about 4 years earlier. Now, from all of this work, it sure does look a lot like this phlogiston hypothesis has a lot going for it, doesn't it? Doesn't it? I mean, you've all heard of phlogiston, haven't you? I mean, just yesterday my wife said to me, "Hey, I'm going down to the store. Do we need anything?" And I responded, "Oh yeah, hey, I'm out of phlogiston. Can you pick me some up?" Well, okay, maybe not. So maybe you haven't heard of this stuff before. And maybe you haven't heard of all of these other different types of airs either. I mean, what gives? We've got fixed air, phlogistated air, inflammable air, which is really pure phlogiston, nitrous air, dephlogistated nitrous air, and just plain old dephlogistated air. Plus, I'm sure Priestley had names for about 4 or 5 other gases and airs that he had created in the course of his experimentation. So where does that leave us? One of my goals in this podcast is to try to communicate just a bit of the process of what really happens when people wade into a new area of investigation and have to try to make sense of it all. Hypotheses get created that are usually just modifications of older hypotheses. New phenomena get discovered that aren't very well understood at first. People stumble across weird things they don't expect. All kinds of things get strange names because researchers don't really know what they're looking at. It's all part of the process, and it's jumbled and it's chaotic, and it looks a bit like one might find in a Lewis Carroll book. And yet, information is still being produced. With each step, there's more knowledge. More pieces of the puzzle are being put on the table, and some of the pieces start to fit together just a bit. Of course, so is the stuff that doesn't seem to fit anywhere. Pieces that look like they belong to a completely different kind of puzzle. What's needed is someone who can step back just a bit and see the bigger picture for what it is. It's that person who walks up to the jigsaw puzzle you've been working on for 2 hours and with fresh eyes takes what you've been trying to put together and rearranges it just so, and all of a sudden things start to resolve in ways you just didn't see before because you were stuck in your old way of thinking about how the pieces should fit. In our story, that person is one Antoine Lavoisier, and he will affect the beginning of the first chemical revolution. Before I talk about him, though, I need to remind you of one thing. We still have this weight issue with the phlogiston hypothesis. Calcination still makes metals heavier, not lighter, and all the attempts to describe phlogiston in such a way that it would explain that result had been shown to be wrong experimentally. At about this time out in Russia, a chemist by the name of Mikhail Lomonosov was heating metal but doing it in an absolutely airtight vacuum chamber. What he found was that there was no weight change, and this led him to conclude that calcination had to be the result of something from the air combining with the metal, when it was hot instead of phlogiston leaving the metal. What this gives is an alternative hypothesis. Maybe all this has to do with gases from the atmosphere combining with or being driven out of substances through merely chemical processes rather than through some form of transmutation. Unfortunately, Lomazanov was in a scientific hinterland out there in Russia at the time, and not many people had heard of his work or took it very seriously. So, back to Lavoisier. Have you ever met that guy who knew he was the smartest guy in the room? And you knew it too? And he knew that you knew? That guy was Lavoisier. He wasn't particularly arrogant or haughty necessarily, but he was really smart, and he had no problem demonstrating his brilliance with a competence that got everybody's attention right from the start of his career. His first brilliant work was to conclusively show that water could not be transmuted into earth as had been previously thought. If you think about leaving a glass with just a bit of water out on the counter for a few days, when you come back, the water's gone and there's a residue left in the bottom of the glass, which is especially true for those of you who live in areas that have hard water. What was thought was that the exposure to air and light caused the water to transmute into earth. Lavoisier took a container, put distilled water into it, and then sealed it up tight so nothing could get in or out. Then he heated the container for 101 days and weighed everything, and there was no change. He did find some flaky stuff in the water, but when he weighed the water and dry containers separately, he found that the glass container had lost the same weight as the flakes that he had found, and correctly concluded that the stuff had come from the container itself. This also showed that the mass hadn't changed, and it meant that Lavoisier's equipment was up to the task of accurately measuring the weights of the things he was studying. Once he was assured of this, Lavoisier began to repeat the experiments done by a number of pneumatic chemists, but this time he made more exacting measurements of weights gained and lost. By doing this, he demonstrated beyond question that the weight does not change in chemical reactions, thus establishing what we now call conservation of mass. And as we've discussed, a lot of these reactions either produced various airs or seemed to absorb them. As Lavoisier conducted these researches, he began to recognize that the entire framework of chemistry was built on a faulty foundation, namely that of phlogiston. Rather than this substance being released, he suggested that combustion and calcination were a combination of material with the new gas he claimed to have discovered, oxygen. I'll release a supplement regarding the scientific controversy regarding the discovery of oxygen, which, as I've already mentioned, both Priestley and Shell have already produced in their researches, the former calling it dephlogistated air, while the latter called it fire air. The key point here is that it was Lavoisier who understood that this was something different than just common air. Priestley and Shell thought it was that what they had produced was common air with the phlogiston removed. But what Lavoisier had recognized that this was a completely different thing. Like Cavendish, he found that common air was a mixture of different gases, and that this was the one that interacted with things during combustion, respiration, which he had shown to be a form of combustion, and calcination. He named the new gas oxygen from the Greek for acid former, because he mistakenly thought that all acids had to possess this new element. In doing this, he was able to explain over a century of chemical work in terms of not some metaphysical or mystical material like phlogiston, but with a substance that could be weighed and accounted for. Additionally, he was able to isolate Cavendish's inflammable air as another gas rather than as the substance phlogiston itself, naming the gas hydrogen, again from the Greek, this time meaning water former. Lavoisier was able to run the water-forming reaction of hydrogen and oxygen forwards to create water in a 2-to-1 volume ratio, and backwards to turn water into hydrogen and oxygen. In this, Lavoisier demolishes the phlogiston hypothesis and moved chemistry onto a fully scientific footing. It is the work of Lavoisier that once and for all relegates the field of alchemy to the footnotes of history and the realms of pseudoscience. However, before we move on, we should note that the phlogiston hypothesis plays a really important role in building a bridge between the researchers of alchemy and those that establish chemistry. While phlogiston doesn't exist, Becker's idea gave researchers something tangible to search for. It was a mechanism to explain phenomena, and it allowed experimental work to be done in order to find it. It gave a principle around which to organize one's thinking and allowed for testable predictions to be made. Finally, as a hypothesis, it was something to offer an alternative to that allowed chemists to make distinctions and thus progress. The whole thing may seem a bit silly now, but it's hard to imagine how pneumatic chemists would have gotten very far without it, and how Lavoisier and Lomazanov would have been able to establish a completely different explanation. As I said in the episode on scientific ideas, hypotheses don't have to be right. They just have to allow chemists to devise ways to test them. Even if they're ultimately shown to be wrong, in that way they allow for progress to be made. Before we leave this subject, I would be remiss not to mention Lavoisier's other big contribution to the discussion, and that is a wholesale revision of chemical nomenclature. At this point, chemistry is mired in a muck of old alchemical names and terms that obscure the underlying structure of chemical combination reaction. Working with 4 colleagues, Lavoisier sweeps all of this away and adopts a common naming system for things, such as oxides for metals that have combined with oxygen, and carbonates for materials from which carbonic gases can be liberated from. This system, much like his disproving of phlogiston, will meet a good bit of resistance initially from the scientific community. But it's so powerful and helpful that his new organizational scheme eventually gets adopted and is still used with some modification today. Unlike others that I've mentioned in this podcast, Lavoisier will not meet a happy end. Caught up in the destructive energy of the French Revolution, Lavoisier will be guillotined in 1794, just as he's beginning his research on human respirations. His ideas lay at the foundation for understanding the true nature of chemical reactions and make it possible to develop a theory to explain them based on a new definition of the atom. As I close out this podcast, I really need to share a couple of sources with you so you kind of know where I got some of my information. The 2 biggest inputs I've had for this podcast are a couple of books that you can go out and find at your various booksellers that I think are just excellent. The first is Bernard Jaffe's book, Crucibles, The Story of Chemistry from Ancient Alchemy to Nuclear Fission. And the second is a book called Creations of Fire, Chemistry's Lively History from Alchemy to the Atomic Age by Kathy Cobb and Harold Goldwhite. Both of these sources have just been really, really helpful for me to understand and to communicate not only the chemistry being done, but the biographical information behind some of the individuals that we've discussed today. Since this podcast is so long already, I've had to leave a lot of stuff out. You might want to go and check the 2 sources out to see if there's some more information you'd like to see, or if you're just interested in this, there's just a wealth of information in there. If what I've covered seems interesting, go out and take a look and see if you'd like to read them on your own. These will also form the basis of a supplemental episode I plan to release where I cover the question of who should be credited with the discovery of oxygen and the issue, more broadly, of scientific primacy of discovery. So until next time, full sails on your journey.